Hello guys. Okay. So for this problem, I reduced the whole paragraph problem about the building and just put like a better like a mathematical more concise mathematical um, reduced problem with the same basis basically. So I rewrote it as given the curve z equals -100 natural log of r, find the volume of the region bounded by the xy plane and the revolution of the curve about the z-axis. Then calculate the surface area. So basically, this is very similar to what you have to do in the problem, except for one thing that in the problem they ask you to compare if there is enough volume to build the actual tower or the pyramid, right? In this case, I just added a new component to it, which is just calculate the surface area of such a building, right? Such a tower. The methods I used. Okay, so I used this method by solving for r and integrating on z-axis. Basically, I could have also done a cylindrical shell method, but to be honest, I chose this method because the integrand becomes easier to solve. Then using limits, I evaluated the volume. So I use limits because obviously z ranges from 0 all the way to infinity. So I'm not just going to write an informal integral as 0 to infinity, but just use limit notation. Then for the surface area, I obviously use the surface area formula. And obviously the surface area formula comes always as a, the f of x always comes as a y coordinate. But you can always have the option to switch around the variables, the y as the independent variable and the x as the dependent variable. So in this case, I switched the roles between z and r, right? And I basically put the independent variable as z again and use r as the dependent variable. So I use that formula to find the superficial area. Just give me a second. Yes. And then I use the z-axis, like I said, for the integration, and then use integration by parts for some of the integrals for the surface area until it gets simplified. So I'm just going to show you real quick what I did in document 2. Basically, this is the description of the solid of revolution, which depicts the tower that we're talking about in the problem. I did it on a three-dimensional space, calling z the height and r the radial distance for the revolution. In pink, I have the formula for the disk method, and and then the black ink is all the algebra. In blue ink, I solved for r, and then the result was 50 pi for the volume. Obviously, the units for this is unitless unless the function or the original function y equals -100 natural log of x has specific units, right? Then for the area part, surface area part, the formula becomes, like I said, I put it in terms of r as the dependent variable and z as the independent variable. So then we're integrating along z-axis. The formula is in pink, part of it informal. And then I formalize it in when I'm doing the algebra as limit goes from b to infinity, 0 to b, of all the whole expression, right? And the reason why I chose this this type of order for independent variable and dependent variable is because the integrand becomes even more easy to to solve by noticing that we can do use substitution like it did in this case, change the limits of integration again, and now you have something that looks like can be solved by using trigonometric substitution, which I will show you guys in the next page right here. Okay, so in this page, basically what I did is I did trigonometric substitution. I used identity tangent squared theta plus 1 equals secant squared theta. I did another use substitution, right, to put that to put that 1 over 10 to the, 1 over 10 square, I believe. Or it was, yeah, it was 1 over 10 square u square, I believe. And then I did the substitution for u equals 10 squared tangent theta, which then simplifies everything to, 20,000 pi, and I go from 0 to tangent inverse of 10 to the negative 2. By the way, all these limits I calculated independently again. I changed the limits of integration every time you change the variable, and reduces to secant cube theta. So now the challenge here is to find the integral of secant cube theta. And I did this by separating one secant theta from the secant cube theta. And then I approached the problem using integration by parts. Then it turns out that you do simplify the process, and you do get another integral of secant cube theta, which you can then add on both sides, right? Combine the terms, and then your integral ends up being a function of the integral of only a secant theta, which has a direct integral, which is natural log secant theta plus tangent theta. After doing all this, you basically solve for secant cube theta, and that's 1/2 of the whole expression that I just mentioned. Simplifying all this, then the area becomes 10,000 pi times the evaluation of the result of the integral from 0 to tangent inverse of 10 to negative 2. After simplifying this, there's a little trick right here. It seems like the 10 to negative 2 is way smaller compared to the 1, so it seems easier or intuitive to just neglect the term compared to 1 and assume the natural log of 1 is 0. But after careful consideration, it does make a difference to the natural log if you add the 10 to negative 2 to 1. And that comes out to that 0.01. It does make a difference once you subtract it for 1 over 10 squared, and definitely makes a difference when you multiply that times 10,000, which results in 0.5 pi, or approximately pi over 2. So that will be the answer for the surface area.